Hello, folks. This is Science Talk. I am your host, Jim Massa. Now, I want to discuss with you what you see right here in the headline. Climate change is pushing giant ocean currents poleward. A new study identifies fundamental changes in ocean circulation with potentially dire effects on food supplies, sea level, and weather in densely populated areas. And the caption on this very nice photo of the wave breaking with a seagull there, and you can see a structure in the background for scale purposes, I guess. Wind-driven ocean currents are changing in a warming climate, which will affect sea level rise and fisheries. The world's major wind-driven ocean currents are moving towards the poles at a rate of about 1 mile every 2 years, potentially depriving important coastal fishing waters of important nutrients, raising the risk of sea level rise, extreme storms, and heat waves for some adjacent land areas. The shift was identified in a new study by researchers with the Alfred Wegener Institute, AWI, at the Helmholtz Center for Polar and Marine Research in Bremerhaven, Germany, and published in the journal Geophysical Research Letters. AWI is a world-renowned research institution into climate change. They do a lot of excellent work. Poleward shift is bad news for the east coast of the U.S. because it makes sea level rise even worse. At about 40 degrees latitude north and south, where the effects of the shifting currents are most evident, sea level rise is already 8 to 12 inches more than in other regions, said lead author Hu Yang. On the west coast, salmon being pushed out of traditional fishing waters. In densely populated coastal Asia, the changes could unleash more intense rainstorms. The shift also makes heat waves more likely in subtropical areas. Not tropical, but subtropical, starting getting to around the 30-degree plus north-south latitude area. 8 major wind-driven ocean currents, known as gyres, circulate around vast areas of the ocean. 3 in the Pacific, 3 in the Atlantic, 1 each in the Indian and Antarctic oceans. Antarctic Ocean, also the Southern Ocean. That's this little gyre right here. The rest, you got the circumpolar, Antarctic circumpolar current. That's right around centered on 60 degrees south latitude and just rings around the continent. The rotating currents shape the weather and ocean ecosystem in coastal regions where parts of the current have regional names like the Gulf Stream along the east coast of the U.S. That would be this one. Now, so here's showing diagrammatically the ocean gyres. Okay. Now they said 3 in the Atlantic. Let's count them. South Atlantic, North Atlantic, and this little guy up here. Okay, so that's the Greenland gyre. In the Pacific, okay, you got the North Pacific, South Pacific, and number 3 in the Pacific is this in the Gulf of Alaska. Now, these 2 smaller gyres are very significant, as I will discuss later. Here's the one in the Indian Ocean, and here's the one I alluded to in the Antarctic region. This is the western edge of this gyre here. Same thing for that side there. Now, when I talk about wind-driven, basically the wind pushes on the water, causes the water to pile up. Then that creates pressure gradient, because if the water is higher in some regions and then in others, the region where the water is higher has a greater pressure exerting on the column below it than where it's lower, and water is going to flow down the pressure gradient. And as it goes down the pressure gradient, Coriolis acts upon it. The Coriolis effect, not a force, it's an effect, causes deflection of movement to the right in the northern hemisphere, to the left in the southern hemisphere. So we look at this, okay, he's got the wind pushing the water, and that ties into the trade winds, that ties into the westerlies, and so forth. So the wind pushes on that, You get it helps with what's called Western intensification. This current here is narrower, but deeper, but faster than this current here. It tends to slow down here. This current here is wider, doesn't go as deep, and is slower moving. But as the water is flowing, okay, you're going to have Coriolis, creating a deflection to the right, as indicated by the arrows here. And the arrows tell you the direction. So this is clockwise. This is counterclockwise. All the major ocean gyres in the southern hemisphere are counterclockwise. In the northern hemisphere, they're clockwise. So it pushes, and then you're going to have water also piling up. This is from the water flow itself. So you have wind pushing the water to piling up, and then the water movement is going to cause piling up because it's going to go to the right this way. It's going to go to the right this way. It piles up in the center, creates what's called a convergent zone. So what happens in the middle of the convergent zone? The water sinks vertically, called a downwelling. And lots of times you find that these gyres are basic self-perpetuating systems. Now in the southern hemisphere, core goes to the left. So the water's moving this way, it's going to deflect to the left, to the left. Get the same situation, a convergent zone in the middle with a downwelling. In the middle of the major oceanic gyres, the middle where convergent zones tend to be biological deserts. So now let's look at the situation here in the Gulf of Alaska and up here off the eastern Greenland, up by Svalbard Island and so forth. Water is going counterclockwise, right? Motion is counterclockwise. Deflection is to the right, so the water is going to go that way. It's going to go that way. Leaves a void in the middle. Well, continuity of volume. You have to replenish that. You get an upwelling in the middle of this little gyre here, as is also here. Same thing here in the Gulf of Alaska. That upwelling brings nutrients. It is no accident that these two gyres are very productive. And by the way, with movement to the right, and same thing here with movement to the right, you get a phenomenon called onshore Ekman transport, which also brings nutrients onto the shelf, and so forth, also helping the productivity of those communities. So what they're basically saying is that we look at the center, that all these currents are being shifted northward. So when you look at here, you might have water moving this way. You're going to have an upwelling here, another little bit of, to a lesser degree of onshore Ekman. But you're going to have upwelling bring in nutrients, which helps the marine ecosystem with their productivity this way. If you start shifting this northward, you change the physics, the physical dynamics of things, and you're basically going to get less productivity. That's what they're saying. So we're seeing a shift to the north this way. We're seeing a shift to the south this way, i.e. towards higher latitudes. Now, I'm just giving a very brief overview here explaining these gyres. If you really want to know more information, I made a video that's lengthy. It's called Rotating Systems. I explain not only oceanic gyres, but I explain high pressure systems, low pressure systems in the atmosphere. I discuss Ekman transport, onshore Ekman transport, Ekman spiral. I explain all that in great detail. So if you're interested in learning the great details of how gyres operate, the physics of it, if you will, please check out that video. A lot of it is derived from pressure gradient, whether it's in the air, high pressure, low pressure. In the water, pressure gradient, with the water height, setting up pressure gradient that sets the water in motion, which then Coriolis acts upon, in addition to wind forcing. So what we see is the key to forming these rotating systems is basically differences in pressure. And in the case of the atmosphere, and to a certain extent in the water as well, the differences are also in pressure are driven by differences in temperature. Blue lines are cold water. red lines are warm currents. So cold current, warm current. This is the Labrador current. There's Labrador coming down this way, bringing in lots of icebergs into the North Atlantic. This is about the epicenter for the North Atlantic Oscillation, by the way. So basically what they're saying is we're shifting these here. Now, little point here. You've heard me discuss this before in my other videos. The Gulf Stream becomes the North Polar drift here, the northward drift here. Here's the Jin Sea location, Greenland, Icelandic, Norwegian Sea. This gives off its heat. This is what keeps the UK and Scandinavia having moderate temperatures. It gives off its heat, becomes cold. It's already salty to begin with. It's cold, salty, very dense water. It sinks. It sinks down to about 1,500 meters and returns south, called the North Atlantic Deep Water. This is the Atlantic Meridional Overturn Circulation, and to start what's colloquially called the conveyor belt. Well, the conveyor belt is slowing down. So when this sinks, it pulls the Gulf Stream with it. It's slowing down. The Gulf Stream is also slowing down. But more importantly, this is bringing warmth from lower latitudes to high latitudes, and then this is bringing cold water from northern latitudes to lower latitudes. So it's a heat distribution mechanism for the planet. So this is what's going on with the gyres, and we are seeing the shift in the center of the gyres moving northward, will then affect the physical processes that then affect biological productivity. So they basically looked at 40 years of satellite measurements of sea levels and surface temperatures to ascertain how the gyres are changing. Because the poleward shift changes the distribution of water across the oceans. Now, it's difficult to get actual sea level heights and actual currents. Well, you can stick flow meters in there, but you have to deploy quite a bit of it. So what they do is they deduce the position of the currents and their movements by looking at sea level heights, the differences between warmer and cooler ocean, and other parameters. And the satellites clearly show how the sharp boundary between warmer and cooler ocean gyres have shifted towards the pole. The movement of these ocean fronts help identify the position of the ocean gyres. Some of the currents run close to densely populated areas, including coastal China and Japan, Argentina, and eastern Australia. And the impacts of the change will be felt strongly in these areas, Yang said. So let's go back up to hear what they're talking about. They're talking about these currents here. These are going to move around. They're going to affect how nutrients are distributed, where the currents are found, and it's going to affect the productivity. This is off the coast of Argentina. Same situation here, and then eastern Australia, same situation. Important fishing communities here. People are reliant on resources from the sea in those areas. Some of the current, okay, we already talked about it. At the western edge, gyres move warmth and moisture from the tropics to higher latitudes, which affects air temperature and rainfall. I've already alluded to that in my discussion of the Gulf Stream as an example. The shift is likely to drive more extreme heat waves in many subtropical regions as warmer water and air from the tropics move to the pole. The study suggests ocean current shifts will squeeze commercially important fisheries, especially in the Pacific Ocean. If you move the temperature gradient toward a higher latitude, the cold water species do not have a lot of room to escape. The North Pacific is blocked by continents. There's no space for fish to retreat. This partly explains a trend of declining and rapidly shifting fisheries that have been documented. Now, I've done videos where I discuss how the warming ocean is causing fish to move northward or deeper. So this is a ramification of that, and this is all tied in. Fisheries decline in the South Atlantic off the coast of Argentina, documented as long as 10 years ago. may be also linked with the southward movement of the South Atlantic Gyre as the shift rapidly warms the ocean in that region. Don't forget, if you have slightly warmer water there, you're going to have you're going to reduce any vertical movement, minimize any vertical mixing, which is important to bring in nutrients. Across the Atlantic along the southwestern coast of Africa, the shift is also affecting the eastern edge of the South Atlantic Gyre, where the Benguela current drives cold, nutrient-rich water from the depths of the oceans to the surface, which provides lots of material for the algae and plankton to increase their productivity, i.e. get blooms. Those blooms then feed the zooplankton, the fish, etc. So they're talking about this region here, okay, on the eastern edge of the South Atlantic Gyre off the western coast of Africa. And geologic clues from the last ice age about 20,000 years ago include ocean bottom sediments. Such paleoclimate evidence can show the paths of the boundary currents shifting as global temperatures change. Sediment deposits on the ocean floor show that during that period, the Agulhas current, flowing south along the east coast of Africa, was 800 kilometers from its present position. That's about 7 degrees latitude. So they are referring to this current right here. The Agulhas right there. And by the way, a little note here. If you look right on the equator, the currents are pretty much running in a straight line because there's no Coriolis acting upon it. The degree of deflection is a function of latitude. It's 0 on the equator. It's strongest at the poles. So what are they talking about here with the geologic clues? They're looking at isotopes. They're looking at isotopic fractionation, C13, C12 ratios, N15, N14, O18, O16, to a lesser extent, O17, O16. So they're looking at these fractionations and they're able to reconstruct past climates, reconstruct temperature profiles of the past, as well as ascertain current movement, whether there was deep water flowing or not, whether it was where the positions of the currents were, and other aspects. We can reconstruct all of that. I did a lengthy video on isotopic fractionation where I go into great detail explaining how the isotopic fractionation is used to ascertain everything I just mentioned. Past temperatures and CO2 levels, where the currents were, where there's deep water formation, productivity, that kind of stuff. So to get more information on all that I am discussing here, all tied together, look at my rotating systems video, look at my isotopic fractionation video. Go to my page, click on videos, and scroll down, and you'll find them there. Ocean currents also distribute the eggs and larvae of marine organisms over wide areas, so the shift of the gyre is likely to affect the distribution of many species. There are signs of similar changes all over the world. In Antarctica, for example, a 2019 study tracked a rapid poleward shift of krill as the region warms. At the same time, research shows southern hemisphere subpolar westerly winds are intensifying and also moving poleward. I discussed the major wind patterns, the westerlies, the trade winds, etc., in my rotating systems video. In the northern hemisphere, the Gulf Stream has shifted northward, and that has chased cod out of the Gulf of Maine. Not only has it shifted northward, but it's also slowing down, as I mentioned earlier. So let's look here. This is basically the Gulf of Maine, right about where that finger is. I mean, this is Nova Scotia here. Okay, there's Newfoundland, Labrador. Okay, so you have the Georges Bank here, which is in the days it was a very highly productive fishing ground. So you can find cod, pollock, haddock, main fish staples. Up here in this region here, southern tip of Greenland, is the Grand Banks. Major uh, fishing area. It was basically commercially extinct in the 90s, where all fishing was stopped. I've heard they've since reopened it as it has recovered, but they basically caught all the fish there. And of course, we have this region here where the Scandinavian folks go to obtain fish. But this is the Gulf of Maine. Cod are moving out because if this water is warming and they want to get out of there to cooler waters, that's going to decrease the catch per unit effort, as fisheries biologists use that term to ascertain fishing success for the commercial fishermen. So that also ties in when I said when fish are moving further north because the water's getting too warm for them. Previous research by Yang and other scientists also have shown that coastal currents associated with the major gyres are in sync with global warming, transporting more heat, pushing more intense storms toward the coast of Asia. Some of the movements detected in the study is partly due to natural fluctuations, but climate models that include greenhouse gas concentrations in the equation, probably should be plural equations, suggests the observed changes are most likely to be a response to global warming. The climate models with high atmospheric CO2 levels produced the same trends we saw in the satellite data, AWI climate model and co-author Garrett Lohman said. Simulating climates with different CO2 levels enabled the researchers to separate the influence of greenhouse gas warming from natural variations. So let's pause there for a moment. You've heard me discuss this many times before. A couple of things. Keep working the models until they very accurately reproduce what has already been observed. And we get to at least a minimum of 95% confidence. This statement here, when they change the CO2 levels, what they're doing is they are accounting for natural signals and anthropogenic signals. They're separating it out. So when people say the models don't tell you the difference between that, they don't know what they're talking about. Scientists take that into consideration, and we calculate for it. We model for it. So basically what the bottom line is that what they're saying is we've accounted for natural cycles, and what we're left with is that these changes observed, the observed response is a result of burning fossil fuels, i.e. human activity. Yang said there's no reason to think the changes will slow down or stop anytime soon. As long as the global temperature keeps increasing, this movement of the currents cannot really stop due to thermal inertia because the climate is not in equilibrium with CO2 levels. Now, this goes back to the concept I have repeatedly said on this channel. Humans have perturbed the system. The system is continuously looking or trying to settle on its new equilibrium state. But because we continue to perturb the system, that cannot happen. So the system itself is in a continual state of perturbation and thus cannot find equilibrium. Think to the idea of chaos theory. Any slight changes in initial conditions, any different little minor perturbations in initial condition will yield vastly different results down the line. That's kind of what's going on here. This is basically chaos theory in action. So because humans have perturbed the system cannot find its equilibrium, and continual perturbations makes it even more difficult. So the bottom line is we have strong evidence that human activity is now causing the ocean gyres to shift their locations in the ocean. This will have adverse effects on biological productivity, which will then impact the available resources that humans can harvest. And I'm putting aside the population question for the moment. And also it will change, it will bring heat waves to subtropical regions. It can change rainfalls. It can change movement of nutrients onto the shelf, etc., etc. So once again, please check out my rotational systems video, my isotopic fractionation video for much, much more detailed information. And you'll then see how this is tied into this report I just shared with you. So thank you for your time. And I hope you found this video interesting and informative. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.